Good morning or good afternoon, wherever you are. Welcome to today's IEAGHG webinar on the recently published study, Managing the Transition of Depleted Oil and Gas Fields to CO2 Storage. I'll just wait a few minutes while people enter via the lobby, just before we get started. Okay, my name is Nikki Clark and I'm the Senior Geologist at IEAGHG, and I'm very pleased to welcome you to today's webinar. Today we'll be joined by Philip Neal and Wouter Janssen from TNO, and Brad Lingo from Pilot Energy, and Marcel Bouts from Porthos, who I will introduce shortly. A quick note on webinar procedures for today. As attendees, your mics will stay muted throughout. If you have a question for the speaker, please add it to the chat box and we'll address those at the end of the webinar or during if we're able to. And please also note that the webinar is being recorded and will be made available on our YouTube channel after the event. I'll begin this webinar by presenting a short overview of IEAGHG, followed by a brief background and motivation to the study. And I'll be then joined by my co-presenters, Philip Neal and Wouter Janssen, to give an overview of the report and the main findings. And then there'll be two case studies, one from Australia, presented by Brad Lingo, and one from Porthos in the Netherlands, presented by Marcel Bouts. And we'll wrap up the webinar with a time for question and answers. So the IEA Greenhouse Gas R&D Programme, IEAGHG, is an international programme that evaluates mitigation options for greenhouse gas reduction and has a programme focus on carbon capture and storage. Firstly, I'll just show this short disclaimer slide that we show at the beginning of all our presentations. So IEAGHG is a collaborative international research programme founded under the International Energy Agency in 1991 and is functionally and legally autonomous from the IEA. The IEAGHG are a members-based organisation, and thanks to their support, we can fund our research activities. We currently have 38 members comprising countries, companies and organisations, and our members steer the direction of our research programme. IEAGHG helps facilitate knowledge sharing and connecting people through a number of pathways. Our main activities comprise commissioning technical studies such as this one, with over 360 studies published via our website. We hold network workshops, which you can find out about via our newsletter or our events page. We host the GHGT conference, which is coming to Australia next year in 2026, an international summer school with over 700 alumni from 60 countries, which is an annual event, and through external involvement with organisations such as the UNFCCC, IPCC, London Convention and ISO, etc. So on to our study. What was the motivation for this study, managing the transition of depleted oil and gas fields for CO2 storage? Depleted oil and gas fields can be attractive for CO2 storage sites, especially when they're in proximity to large-scale sources of industrial emissions. And the advantages are that they're well characterised, have infrastructure in place, and could delay or defer decommissioning. So a smooth transition from hydrocarbon production to CO2 storage site requires alignment on multiple levels. So this study aims to explore the major issues involved in such transfer: technical, economic, regulatory and commercial factors, provide recommendations on ways to overcome barriers and maximise opportunity. And they also do this by exploring a number of case studies, two of which will be presented today. The study was conducted by TNO. We're glad to have Philip today here with us, and the other authors are listed. The report was published for our members in August. All our reports are available to our members for 6 months and then are publicly available. So this report's now available on our website, and you can explore all our reports on our publication library. So we're very pleased to welcome our presenters of today's webinar. Philip Neal of TNO is a senior project manager and has been active in the field of CCS for over 20 years. Wouter Janssen, also at TNO, is a researcher in the Geoscience and Technology Department and has a background in geophysics. And prior to joining TNO, he was a CCS policy officer in the Dutch government. Brad Lingo is the Executive Chairman of Pilot Energy Limited with a career of over 40 years. He's got extensive experience in formulating and implementing growth strategies to create and maximise value across the energy value chain, from the energy resource through to the point of energy utilisation, with a current focus on the energy transition and delivering both clean and cost competitive energy solutions for both domestic and global markets. And Marcel Bouts is a consultant senior production engineer with more than 40 years experience in the energy sector, mainly gas and oil, but also geothermal projects and CCS. And since 2021, he's been working on projects for EBN, and his main focus is a Porthos CCS project offshore the Netherlands. So I will hand over now to Philip and Wouter for the next part of this slide.
Thank you, Nikki, for the introduction. So, and also thank you for giving us the opportunity to do this study. I think this study is quite timely. We see a strong increase in the number of projects worldwide. Next slide, please, Nikki. On the next slide. Yeah, thank you. On the next slide, we have copied a number of maps. No, sorry, the previous one. Yeah. We've copied a number of maps from the Global Status Report published by the Global CCS Institute. And these maps show that the number of projects acting in various parts of the CCS chain is rapidly increasing. There are many projects out there. And I think it's fair to say that the number of projects actually developing depleted fields for storage is also increasing. Especially in our region of the world, the North Sea, we have many fields that are already depleted or will be in the coming years. And I think a while back, these depleted fields were looked upon as potentially very attractive targets to be converted from production to storage. And I think it's also fair to say that the projects developing depleted fields have started to discover that that conversion may actually be quite challenging. So, as you may know, in Europe we have a legal target to reach an injection capacity of close to 50 million tons per year by 2030. I think we're not going to reach that target, but at the same time, I think we're going to be, well, let's say in the neighborhood by 2030. And I think depleted fields are going to be a significant part of that capacity. You may also know that if we look at things worldwide, then estimated capacities in aquifer are expected to be way bigger than those in depleted fields. But still, depleted fields will be attractive. And the current projects are laying the foundation, I think, for future projects by developing approaches, solutions, best practices for use by the next waves of projects. And in our report, we've made the start, perhaps, of trying to look at the different projects and extracting best practices, and perhaps more importantly, extracting insights into what could be done to make the transition from production to storage faster, and which barriers are there to be resolved in the coming years. Now, I will now hand over to my colleague Wouter to give a highlight overview of the report.
Thank you. Could you go to the next slide, please? Thank you. I'll start with going through the setup of the research briefly. This report, it offers an investigation into the barriers you might face when you go from hydrocarbon production to CO2 storage in the same site, in the hope that this information may help smoothen this transition somewhat. We recognize that some of the challenges that we've written down in our report may be resolved by early movers developing best practices at the moment. The report looks at this transition from 4 different angles: technical, economic, regulatory, and commercial. For the remainder of this part of the presentation, I will dive deeper in 3 important aspects, being low reservoir pressure you might encounter, reuse of facilities, and available data from the exploration and the production phase. Next slide, please. Thank you very much. First off, why depleted fields? We see an increasing share of depleted fields in the CCS portfolio worldwide, especially in Northwestern Europe, where we see production fields reaching the end of their economic lifetime. And utilizing these depleted fields may lead to a rapid growth of operational storage capacity. Now, depleted fields have a number of advantages as well as a number of challenges. Advantages being that these fields are a proven reservoir and have proved to contain hydrocarbons, oil or gas, for millions of years. So you know there is some sort of geological structure in place here. Data could be available from the exploration and the production phase. Appraisal times can be much shorter, and hydrocarbon production facilities may potentially be reused. Now, in this report, we've written that down as both an advantage as well as a challenge, because the reuse of facilities is the feasibility of it is very case specific. Other challenges could include, like I said, low pressure in the reservoir, legacy wells, which may form leakage pathways, and the fact that regulators often require abandonment soon after production ends. Next slide, please. As I said, I will dive into these 3 topics: low pressure in the reservoir, the data aspect, and the reuse. And we will start off with the low pressure in the reservoir. Next slide, please. Yes, thank you. The reservoir pressure can be very low after production ends. Occasionally, it goes as low as below 10 bars. And this pressure gap can lead to operational challenges as well as challenges with the containment of the CO2. And this is due to the fact that CO2 expansion effects, or the Joule-Thomson effect, can lead to very strong temperature decreases in the well and the near wellbore area. And it can even lead to sub-zero temperatures. Some risks are associated with these low temperatures, such as the risk to material of the well and the wellhead, such as the freezing of the analysis fluids, or risk to the operation of the subsurface safety valve, risk of shrinking the well casing and main reservoir system, risk of thermal fracturing of the reservoir, risk of hydrate formation, which is in turn dependent on impurities in the CO2 stream. And hydrate formation may lead to issues with the injectivity of the well. Now, considering reservoirs have different porosity, permeability, pressure, or thickness, every well has a limited operational window for safe or effective operations. Now, if you look to the figure on the slide, you see an example of temperature and pressure profiles along a CO2 injection well for 3 different reservoirs. Each reservoir has a different productivity index. It's denoted here as PI, and this is a measure of reservoir permeability and or thickness. In this synthetic case, CO2 conditions at the top of the well are 5 degrees Celsius, and it's pressurized to 120 bar. Now, what you see is that reservoir with the lowest PI value represents a reservoir with either a low permeability or a small thickness. And in the top left panel, you see that injection under these conditions can lead to high and possibly problematic pressure buildup in the well. However, in the case of the reservoirs with higher PI values, or you might call them better quality reservoirs, pressure buildup will less likely form a problem. However, in the top right panel, you see that very low temperatures, sub-zero temperatures, due to the CO2 expansion effects, could lead to problems in the top of the well. Moreover, in the third panel below, you will see two-phase flow in the top of the well for the two better quality reservoirs. Now, this is just meant to give a hint of the complexity of injecting CO2 in depleted reservoirs with a very low pressure. Now, in the development of a depleted field for CO2 storage, it is very important that detailed assessment of CO2 conditions along the transport and storage network should be performed, as well as adequate monitoring plans for CO2 conditions are in place. And the designing of a suitable and safe injection strategy can really be quite a challenge. Next slide, please. Now we go to a separate second topic, which is the reusing of facilities, which in this case quite often is pipelines, wells, platform. The main driver here is cost reduction, which can be quite significant. For the UK offshore, it was estimated to be 20 to 30%. Moreover, reusing hydrocarbon facilities may delay the decommissioning, which is estimated to be 10% of the capex. So that could also be quite a driver. However, the challenge here is that the feasibility of reuse is highly case dependent. Assets are quite often at the end of their design lifetimes and requires a very thorough assessment of the state of the assets. For instance, what the remaining lifetime will be, whether it will be possible to convert them to CO2 injection purposes, what the associated cost will be. For example, wells will need to be checked on the possibility of converting them from production wells to injection wells. Wells may be plugged and abandoned. Wells may not always have the right size, or they may not always be made out of the right material. And in many cases, wells will eventually need to be remediated, or workover will need to be performed. And similarly, where it comes to pipelines, assessment of the remaining lifetime will need to be performed. And here, corrosion status is important, since CO2 streams with certain impurities may be at risk of corrosion. Now, altogether, reusing hydrocarbon facilities may involve costs, and new build could be cheaper or more suitable options, especially constructing new facilities will give the operator also a chance for optimization, for instance, in what location you would place these facilities. Now, when looking at reusing a facility, timing is also an important aspect to avoid maintenance costs, deterioration of the assets, or loss of integrity with the assets. It is important that the period between the production and the storage should preferably be minimized. When looking at the regulatory aspects, we see that some guidelines for reuse are yet to be developed in many countries. This is not for all countries. For example, the UK is quite advanced. However, the Netherlands does not have specific guidelines for reuse, but here they do allow for temporary exemption of dismantling of facilities. After production, operators are required to perform this decommissioning. Currently, we see that reuse is often not being taken into account. However, wells could be abandoned in such a way that there is a higher confidence of integrity when it comes into contact with CO2 later on. Therefore, our report includes a recommendation for competent authorities to develop a regulatory basis for the assessment of the reuse of assets, and as well as adjusting the decommissioning regulation. Now we see first wave of best practices emerging through projects like Portals and Pilot Energy, which will speak after me. And we think it's important that these best practices will feed into these guidelines to be developed. Can we go to the next slide, please? Thank you very much. When looking at CO2 storage in depleted oil or gas fields, we see that one large advantage is the availability of data from the production phase. So this could be in the form of seismics, core samples, reservoir models, etc. There is some understanding of the reservoir and the caprock, which may lead to less data acquisition required, could lead to cost reduction, as well as shorter development times, which are estimated to be between 2 and 4 years compared to a CO2 storage project in the saline aquifer. Challenges here are that reservoir models may need updating or expanding, especially if the storage complex is larger than the area that was modeled for the hydrocarbon production. When it comes to data availability, this should not be an issue if the storage operator is the same entity as the hydrocarbon operator, which is something we observe many times. However, in the case of a transfer of the license, the previous operator does not always have an obligation to share data with the CO2 storage operator. Fields could have been plugged and abandoned a long time ago, and collection and restructuring of data can be especially difficult if the wells have been plugged under a different rule set, for instance, because it has been a long time ago, or if operators have ceased to exist or left the country. In such a case, also access to data can become a concern. Our report includes a recommendation for competent authorities to set up data repositories or develop rules for this data transfer, which arises new questions like what data are we talking about? What would be the level of detail, and how do you manage a risk? How do you make sure you don't end up with an unmanageable amount of data? And here in the EU, we see that the Net Zero Industry Act is already setting forth such a data publication obligation. Can we go to the next slide, please? Very much. Now some conclusions. CO2 injection in depleted hydrocarbon fields can be an attractive option. And as we see from developing projects, that the challenges we have identified do not necessarily have to be deal breakers. Early movers are now establishing best practices, and we believe that at this point, knowledge sharing and capacity building is quite key. Also, we believe continued research and development is required to further decrease the cost, increase the efficiency, and resolve some of the challenges that are still faced. Thank you very much. And with that, I hand over to Brad Lingo from Pilot Energy.
Thank you very much. I'm Brad Lingo, the Executive Chairman of Pilot Energy. We are, next slide. This is an image of our Cliffhead A offshore platform. Next slide, please. So Pilot is developing and converting the end-of-life Cliffhead offshore oil field into a carbon storage project. And that carbon storage project is an integrated project to support not only managing industrial emissions from third parties, but also to support the production of clean ammonia. We are one of a small group of licensed offshore oil and gas operators in Australia, and we're transitioning our current offshore oil production operations to provide a permanent carbon management solution. That Cliffhead Carbon Storage Project is our flagship energy transition project. That initial carbon storage facility will be capable of providing up to 72 million tons of permanent storage, and in targeting first carbon injection rate of up to 1 million tons per annum, growing to 2.5 million tons by 2029, with continuous operation through 2050. And there is significant expansion potential to increase the storage capacity to over 100 million tons and at an injection rate of 5 million tons per annum by 2030. We have achieved the first stage Australian Commonwealth Government regulatory approval, and we've completed pre-feed for the project. The next stage for us is to commence project feed and lodging our carbon injection license and environmental approvals, which is effectively the license to proceed to development. Uniquely, we the regulatory framework in Australia has been in place since 2006 to enable this sort of reutilization and redevelopment of existing hydrocarbon production licenses. But no one had proceeded to even make an application until Pilot lodged the very first application to do so in November 2022. We received that first approval, which is called a declaration of storage formation, saying that we had established that we had identified reservoirs that were proven to be both safe and permanent storage resources for carbon injection. And we were that receipt of that very first applicant and the first to receive that approval in June 2024. Next slide, please. And it really does highlight two particular themes that are highlighted by this the study. That conversion and repurposing of the existing cliffhead facilities is a key enabler for the redevelopment. It is a brownfield redevelopment of the existing cliffhead facilities, minimizing both risk and reducing capex. The estimated replacement cost of those existing facilities is at US $825 million, with a storage capacity of up to 72 million tons and targeting increase to 100 million tons, and that injection capacity of 2.5 million tons per annum, and that regulatory approval. Our development plan focuses on enabling carbon receipts both from onshore and offshore resources, and that reuse of those existing facilities enables us to look at a capex per ton of less than Australian $10 a ton, which we believe makes the project not only technically but economically attractive. Next slide, please. So in terms of the CO2 CRC's assessment of the various carbon storage projects that are being proposed in and around Australia, they've rated 5 projects as in advanced development, and our Cliffhead project is one of those 5 projects. We are the advanced development project that's located in Western Australia, and the West Australian industrial and oil and gas economy is quite carbon intensive, and our focus really is on providing a credible and workable and achievable carbon abatement solution for those high carbon emission industries. Next slide, please. In terms of Cliffhead as an oil field, was quite modest size, about 20 million barrels recoverable. But when we look at its potential as a carbon storage operation and rank it based on annual injection capacity as compared to existing operating carbon injection operations, it is quite significant. And it's going to take a whole lot of these 2.5 to 5 million ton per annum injection projects to really achieve that global target of significant emissions reduction through carbon capture and storage. Next slide, please. So our storage resource and well plan, this is a direct snapshot out of our regulatory submission. And when we look at the Cliffhead field, you can see the designated wells from the Cliffhead production reservoir. There were 8 existing wells in the reservoir, 5 which were oil producers and 3 that were water injectors. And I think that's really one of the key messages around you know, one, getting through the regulatory approval process as the first ever to test the regulatory framework was that we have an injection history. It is the Cliffhead Reservoir is a low energy, low energy aquifer supported reservoir, and through the entire life of the production, all the way through August of last year, the entire production strategy was 100% voidage replacement. So all the water that was ever produced out of the field was reinjected. Makeup water was reinjected. And so that gave us this 17-year plus injection history that we were able to successfully demonstrate. And that's one of those, I guess, future storage resource project opportunities is to look at, what do you know about the reservoir? What do you not know about the reservoir? Not only from a production perspective, but from an injection perspective. And when Cliffhead was originally developed, the original development plan contemplated not only a primary, but secondary and ultimately tertiary recovery. And the production stage that just ended in August of last year was the end of a water flood. And most people that are familiar with CO2 EOR, most CO2 EOR projects are preceded by a successful water flood. And the Cliffhead field has just finished that water flood production stage. And as opposed to then saying, would we proceed to look at the continued development of the Cliffhead oil field through a tertiary EOR, we said, no, actually the right future for this asset is not to pump CO2 into the field to recover more oil, but to use that knowledge of an injection history to simply look at taking Cliffhead from being that warehouse for oil that it had been for millions of years and turning it into a permanent vault for CO2. Our ability to do that analysis, we did start quite early in asking two fundamental questions. One, questions about that knowledge that we had about the reservoir and that ability to essentially remodel the entire field from both a static and dynamic basis, which we were well assisted by CO2 Tech, the consulting engineering arm of CO2 CRC. But the parallel question was how suitable, how feasible was it for the repurposing of the existing infrastructure, both subsurface and above ground. And so that was that first part of the screening process, that asset selection. And both of those gave us a positive set of results to then, one, make that commitment to invest significant capital into first conducting a series of detailed feasibility studies, both techno-econ and commercial. But then once the results of those feasibility studies indicated that we did have a likely feasible project, we then committed to spend even more money to undertake the pre-feed on the project. When we look at the repurposing, and this is a discussion we've had recently with our principal regulators, and I think that's one of the things that's quite important, is that in the Australian regulatory framework, the regulator to look at the future of Cliffhead as a future carbon storage operation are exactly the same regulators that have have all that knowledge and experience of the entire development and production history for Cliffhead. And some of the issues about that are identified in the study about the complexity and of if there's a transfer of operators and is there a seamless transfer of data was greatly simplified in the context of the Cliffhead operation, with Pilot being the co-operator of the field in a relatively small joint venture, but Pilot also being the owner and operator of all the surrounding petroleum exploration acreage, so that we could look at the reservoir resource both within the CO2 injection area and the surrounding reservoirs in the petroleum license area as a common unit from a technical perspective. Moving and talking about that use of the historical data and the need to remodel. When you think about the way, a development of an asset like Cliffhead as an oil field, that those static and dynamic models that were originally developed for the field, though we used those for that initial screening, intrinsically, those models are inward looking. They're looking at how do we maximize the recovery of the hydrocarbons from the known oil-water contact in the case of an oil field. Whereas when you then start looking at the asset from a carbon storage opportunity, you actually have to look at it more broadly and be more outward looking. Because at the end of the day, one of the principal items that you need to be focused on is that migration of the plume, not only at end of injection, but all the way through to where you have fully immobile CO2. So your approach has to be not inward looking, but outward looking. So that was one of the major lessons that we've learned as to how to think about the reservoir. The other major lesson highlighted in the IE study was, what is the interface between injection, use of historical wells, and their suitability for CO2 injection, and do they potentially become leak pathways? The answer is yes. That is a potential outcome. That influenced our entire thought process about how to think about the Cliffhead resource as a storage resource, and our actual strategy evolved over time to say we can actually maximize injection by looking at the broader structure, because we've now learned to look at the accumulation on an outward-looking basis, look at moving the injectors down dip and flankle on the structure. The injectors are all due well, so purpose-built for CO2 injection, and then use some of the existing wells for pressure maintenance, so that we actually look at managing the flow of CO2 and directing it by continuing to use crestal historical production wells to actually remove water. So on effectively a barrel of CO2 equivalent injected in, we pull out a barrel of water. So we're effectively doing and producing from the reservoir in a way that we have done historically, which then maximizes our ability to continue to use and reuse the existing facilities. And so the onshore plant that we produce to, or oil, will continue to do exactly what it's done for the entire life of the operation. But it's producing water not to strip out oil, it's producing water and fluids to effectively manage pressure within the reservoir. and then selecting, one or two of those further more down dip wells to actually become the canary in the coal mine monitoring wells. So of the 8 overall wells, 5 producers and 3 injectors, 4 of the existing wells will be plugged and abandoned, but plugged in and abandoned to a CO2 storage specification, as opposed to how the specification you might apply to simply a low energy depleted oil reservoir. Next slide, please. Then looking at that onshore and offshore CO2 storage architecture. This comes directly out of our pre-feed work with our owner's engineer Genesis. That we really did look at all of those opportunities of being able to receive CO2 from multiple sources, then ultimately aggregating into a header where we can then have a standardized CO2 specification for injection, and looking at being able to receive CO2 by truck, by pipeline, or directly from the blue ammonia facility, as well as then also to take CO2 from marine delivered sources, utilizing the KNCC elevated pressure CO2 transportation solution. Next slide. When we then look at the economic impact of the ability to reuse facilities, as I highlighted, that replacement cost of existing facilities is over US $800 million. When we then look at the incremental additional development cost, it's US $450 million to handle that 72 million tons of create that 72 million tons of storage capacity. So we've effectively reduced the cost down to a third, that if this was just purely a greenfield redevelopment. But it's all fully linked to that, the way we're actually able to reuse, repurpose, and extend the life of those existing facilities. Next slide, please. And then ultimately, that how do we look at reaching out to a lot of the large minerals refining resource CO2 emitters down in the southwest part of WA. Australia has quite a significant resource-based economy. A lot of those resources, whether it's oil and gas, bauxite to alumina refining, iron ore to upgrading, those come, and even battery metals, lithium, precursor material production. All of those come with quite a significant carbon footprint. In Australia, all of those emitters, if you're an emitter of 100,000 tons or more, you're deemed a safeguard facility. Is a safeguard facility. You're required now by law to either offset or abate your CO2 emissions at a declining balance of 4.9% per annum, starting from 2023. And that actually created quite a significant, I think, opportunity to create the regulatory settings to get emitters to be thinking seriously about abatement, because ultimately that declining balance and having to invest in offsets is the stick, but the counterweight to that is anything below that declining baseline in your emissions. If you abate it, you actually create a carbon credit for sale. And the simple math on that is, if you invest in abatement, you create 4 times the revenue opportunity that would greater than your cost of carbon abatement. So for a 1.2 million ton per annum emission source, which there are quite a number of those emission sources in the southwest part of WA, about 350 kilometers south of our storage facility. That facility, based on what is the government's cost containment price, over a 5-year period, would spend about $150 million Australian in buying offsets if they did nothing for abatement. Over that same 5-year period, if they invested in abatement, they would generate $650 million in carbon abatement credits. So we think there's quite an appropriate carrot and stick that then provides those emitters with a commercial driver to actually get serious about carbon reduction, and particularly in WA, where we have a wealth of reservoirs that can be developed, and we're very keen to demonstrate not only the technical veracity of carbon storage to Australian emitters and more globally, but also the commercial paradigm that it just makes good industrial hygiene sense to invest in abatement. Next slide, please. And that's the end.
Thank you so much, Brad. We'll hand over to Marcel now. Thank you.
Yeah, thank you very much. So I'm going to give you some insights, some snapshots of the Porthos project, which is a CO2 storage project in a depleted North Sea gas reservoir. You see a nice picture here of the area where we are constructing at the moment. Because this project has taken FID in 2023, we are now in the execution phase. So we are laying pipelines, building compressor stations, and at the moment the Valaris rig is at the platform where we're going to work over the wells to make them suitable for CO2. So it's going to happen. And when it's going to happen, we're going to inject the first CO2 in mid 2026, so next year. So next slide, please. So I will talk about a bit about the project, but also about operating philosophy and the temperatures we see in a depleted gas field, the well-design drivers and completion selection and qualifications. I will talk about well monitoring during the CO2 injection. And finally, talk a little bit about an integrated injection model we have built to manage those temperatures actually during injection in a depleted gas field. Next slide. Yeah, so this is an animated slide, by the way. So this is actually the west of Netherlands. I'm not sure if you're familiar with the geography, but this is, let's say, 60 kilometers south of Amsterdam. The field is based in the southern North Sea. If you go north, you have the northern North Sea, then you have all those fields from the UK. Now, there are quite a lot of depleted gas fields in this area. What you see here, the purple line is actually the pipeline where the emitters will emit their CO2 in. It's a low pressure pipeline that ends up in the compressor station. And then the next pipeline, which is being laid within a few months, will be a high pressure pipeline to the platform. So if you press another time, you will see these are basically the partners. And the blue one, the blue diamonds are the three partners. It's GasUnie, Port of Rotterdam, and EBN. Those are three state-owned companies who actually are going to manage this project. Then the clients who will supply us with CO2 are Shell, Air Products, Exxon, and Air Liquide. There's a lot of industry there with a lot of CO2. Mainly the CO2 we get here is from steam reforming to generate hydrogen. If you click another time, that also indicates that at the moment the field is and the platform is owned by TACA. It's a license holder, but that will be transferred to the Portos organization when we start injecting CO2. And then next is also that we have subsidies from the European Union. Yeah, so that's basically the overview. If we are now going to the next slide, then we see the platform and let's say a schematic of the reservoir. So it's the P18 platform that's in 25 meters water depth. 4 wells will be converted to CO2 injectors. The other 2 wells will be abandoned. These wells are deviated with a maximum hole deviation of 55 degrees, which is actually quite convenient. So the access to the reservoir is relatively easy. The 2 formations, the 2 reservoirs we're going to inject CO2 are the P18-2 and P18-4 Buntsandstein. That's at about 3,200 meters depth, true vertical. It's a very good reservoir with high productivity, hence high injectivity. The gas was produced from an initial pressure of 375 to where it is now a pressure of 17 bar. So clearly a highly depleted gas field. The current plan is that we're going to store about 37 million tons of CO2, and about 2.5 million tons per year will be supplied by the clients and injected in those 4 wells and distributed over the 2 reservoirs. Next slide, please. So the operating philosophy of Portos is as follows. Since we are dealing with a depleted gas field, so if we would start injecting straight away with a high pressure in the high pressure pipeline, that you see the phase diagram at the right hand side, then we would drop the pressure. We will enter the phase line, and we will end up with a temperature of let's say at -20 in the well, in the reservoir. Obviously you don't want that. So we have the philosophy that first of all we will transport the CO2 warm, that is the heat coming from the compressor. We have an insulated offshore pipeline, and that's more important. We start initially injecting in the gas phase. Yeah. So although we compress the CO2, we're not going to convert yet the CO2 into the dense phase or in the liquid phase, because we're going to increase the reservoir pressure from 70 bar to 50 bar over a period of about 1.5 years by injecting the CO2 in the gas phase. At the moment we are at about 50 bar reservoir pressure. We then switch to dense phase, and we will start injecting the CO2 at higher rates, filling up the 2 reservoirs. Now, at the same time, we will continue to manage the system such that the bottom hole temperature stays above 15 degrees C. That's avoiding hydrate formation. Remember the presentation that Wouter Janssen gave. So that is exactly what we try to avoid, of course. CO2 hydrates. The right bottom picture shows you how actually over time, when reservoir pressure increases, how the phases will change in your well, where you start initially full of gas, and that at some stage you have 2-phase injection, and at a pressure of 250 bar of reservoir pressure, then we will inject everything in the dense phase. So managing this injection is basically done by first starting to inject in the gas phase and then switch to dense phase at 50 bar reservoir pressure. Next phase. Slide, please. Yeah. So for a well design, what are the primary design drivers? Well, because of the low temperatures, yeah, that means that you have to look into your materials and your equipment, make it suitable for low temperatures. Also, there is the possibility that you have higher tension loads on well components, that you have increased thermal cycling. Now, all of that is first of all modeled, yeah, with software, but subsequently we have done a lot of testing of the critical parts of the wells, which will be exposed to those phenomena. So the other thing is, of course, that at the end you have higher pressures in your wells, which is, of course, exactly the opposite if you start producing a field. So it's also something to bear in mind. Now, the other thing is the corrosion resistance. CO2 can be corrosive. It can be very corrosive, of course, if you are in a system which also contains water. Now, for portals, that is less of an issue because this is a very dry gas field. So the risk that we will have CO2 and water when we, for instance, shut in a well is very limited. Then, of course, the cementations. These are wells which were drilled about 30 years ago. So we've done a lot of, let's say, studies to see what the quality of the cement is based on the logs we were taking at the time. But also when we start working over those wells to make them suitable for CO2, we will again start logging the wells and have another check on the cement, especially, of course, cement at the cap rock level. There's a big cap rock of 600, at least 600 meters above this reservoir, so there's a fair chance that it is all sealing. The other thing, of course, the platform and the wells were initially designed for 30 years life, but now we're going to extend it, of course, with 15 to 20 years. So there's a lot of design checks to be done, and of course we'll do that. Now then additional monitoring is required in the wells. In 2 slides I will show you what we will do on monitoring. And then, why are we using actually existing wells? Well, it reduces the risk of re-drilling in highly depleted sandstone. That is, of course, from a technical point of view, also a challenge for drilling. And we assume also that there will be less time and cost required compared to re-drilling those new wells. Next slide. Yeah, so this is everything we're going to change in those wells. The left schematic is when it was producing, and at the right hand side is then when we have worked over those wells. So we're going to install new tubing, corrosion resistant materials of 25 chrome and chrome 13, super chrome 13. Further qualification tests were performed also on couplings, for instance. There will be a new Christmas tree installed, which is also capable of resisting low temperatures, K-rated to call that, minus 60 degrees C, with Inconel cladding, a special alloy. The tubing strings will also tested, as I already said. Multiple cycles were done with low temperatures. Then the subsurface safety valve, that's also mentioned by Wouter initially. That was separately tested, whether it would still function at low temperatures, at minus 20 initially, but also subsequently tested if it was still operational at minus 35. And at the end, we also did a survival test at minus 78. Yeah, so clearly we have done the utmost to make sure that this subsurface safety valve will work. The other thing also mentioned, and you see it a little bit in the schematic, that we're going to place the subsurface safety valve a little bit lower. Initially, they are about 150 meters depth, but we're going now to place it at about 400 to 500 meters depth, because there the temperatures are, let's say, a little bit more higher in case we start injecting cold CO2. So that also helps a bit. We will install pressure and temperature gauges downhole. I will show you in the next slide, but also fiber optics will be used. That's this red line you see along the tubing in the red head side schematic. Elastomers have been tested with manufacturers, and finally the analyst, the A analyst, will be filled with partially with nitrogen, but also with glycol and water. Now the nitrogen cushion is actually an excellent thermal insulator, again to avoid any freezing of the B and C analysts in case we have a low temperature. So as I explained, we will going to reuse wells, so we can replace the fluids in the A analyst, but not in the B and C analysts. So that needs to be protected against low temperatures. So that's why we have about 200 meters of nitrogen cushion in the A analyst. So all of this will be starting soon. The rig is on site and it's going to happen. Next slide, please. I see I have only 1 minute left. So this is about the well monitoring. So at surface we will have gauges to monitor the wellhead pressures, but also the pressures of the A, B, and C analysts. We will measure the injection temperatures, of course, but also each well will have a flow rate meter. Then there will be fiber optics installed to measure temperature along the well, so the so-called DTS. In case there is any leak, you will notice that immediately. It can also help us in testing the SSV, which is mandatory actually every year. At the same time, we also do acoustic sensing. At the moment, as we see it now, we will do that on an intermittent basis, so not continuously. That generates a lot of data, and we are offshore, so we have to transport that data to shore. At the same time, we will think that injecting CO2 and listening whether you have any CO2 flow behind pipe will be difficult, although there are filtering options nowadays available, but we still need to learn that actually. But the installation is there, the integrate the whole let's say equipment is available. And then downhole we have pressure and temperatures, of course that is at packet depth. That all will be transferred to service, and it is also let's equip double equipped, so we have redundancy, double installed. I think the last slide now. 1 minute over time. Oh no, one more. So of course we have the no one back, please. Sorry. Yeah, sorry. So this slides actually shows a screenshot of our integrated injection model. EBN has built this in-house. This basically models the whole system. In oil production and gas production, we are very much familiar with integrated production modeling. Now this is integrated injection modeling, and at the left-hand side you see a block diagram which shows the emitters, the compressors, the pipelines, the wells, and the reservoir. Now everything what we have in the block diagram is also modeled in this system. And also at reservoir level, that at the left-hand side, you see gridded reservoirs, the 2 reservoirs we're going to install that, and the 4 wells. Now, why do we do this? Because we need to manage the injection, especially in the dense phase. We generate what we call operating envelopes, and for each phase in time, basically as the reservoir pressure increases, we generate operating envelopes. Within that envelope, we have to operate the wells, avoiding low temperatures. That's the main concern, of course. So that is why we have developed this tool. At the moment, we are tendering companies to productize this, and hopefully at some stage we can roll this out to other CCS projects where we are involved in as well. Okay, final slide, which is the concluding slide. Yeah. So define is operational philosophy to minimize the low temperature risk. CO2 injection in depleted gas fields has a challenge, and you have to manage that. We do that by increasing the reservoir pressure by injecting gas CO2 before we switch to the CO2 dense phase. Work of the wells will be done to make them suitable for low temperatures. So CRA materials, elastomers will be replaced. SSV has been tested for low temperatures, and the A analysts will be partially filled with a nitrogen cushion. Well monitoring will take place during injection for safe operations. With respect to monitoring, I saw a question somewhere. We will also do monitoring activities at the seabed. We will do baseline monitoring first. We will look for pock marks with the ROV. We will also do CO2 measurements with a probe, and we will also look at other options. Seismicity, for instance, will be monitored. So there will be a lot of service monitoring also in place at the seabed. In case there is an issue, we can then analyze whether what could be the problem. And finally, we managed the injection using an integrated injection model and thereby avoiding operations at low temperatures. And basically, I had to rush a bit because of time, but this concludes my presentation.
Thank you so much, Marcel, and thank you to Brad and to Philip and Wouter as well. I realised that it was very interesting, and I think that it's great that we've used a full complement of time, given that we've covered both the report and also these two projects in development. So it's really good to see practical examples of how this is in progress. So really, thank you for that. Thank you, Philip, as well, for answering a lot of the questions in the chat box as we've gone along. That's really great. I wonder whether, Brad, would you be available? There's quite a few questions for you, so I just wanted to pick out one or two just now. We'll spend just maybe if you could keep it brief for a couple of minutes, and then we'll close.
Yep, absolutely.
So I think I'll just pick out one of the ones, and the others I can forward to you, and you could answer individually. But so I think we had a question. What was the date of when you plan to inject? How are you going to monitor the site, and what will you do with the produced water? If you could just answer those, that would be fantastic, and then we'll make a close.
So I'll start with produced water. We have an existing. Getting a little bit of feedback. Our existing water, our existing onshore plant has 35,000 barrels a day of total fluids handling capacity. When we stopped production at Cliffhead, we were producing 13,500 barrels of total fluids with basically a 1 to 2% oil cut. So we're quite experienced in handling water. Initially, we're starting this year, we'd received a CCS grant from the Commonwealth government, and we're trialing a water treatment technology by a company called Capture 6, and it's electrodialysis system. The produced water will have a salinity of about 65% of that of seawater, and the technology will enable us to effectively, the outcome we're expecting from the technologies, to produce what's going to be a relatively clean industrial water source. As you can appreciate, Australia is a very dry continent, so there's actually quite a significant demand for additional industrial and agricultural water for use. But what's unique about the Capture 6 technology is that the brine recovered from that technology actually is used to produce sodium carbonate as the primary material for direct air capture. And so it's a dual technology that provides not only the water treatment and water processing that we need, but it also provides an additional CO2 capture stream that will then be available for injection to the reservoir. Ultimately, when the blue ammonia plant proceeds, that all the water produced at approximately 27,000 barrels of total fluids production a day, that all of that water will be consumed for industrial cooling by the ammonia plant. We also have an onshore water disposal well that we've used in the past. We have a license for within our existing production facility. The other, I think one of the other questions, so hopefully that answers, and we have also formed a joint venture with the First Nations people of our operating area, the IEAGHG Nation. We have that joint venture in place with the IEAGHG Water Corporation. So they'll actually work with us to commercialize that produced water stream once it's been cleaned up to an agricultural or industrial spec.
That's great, thank you. Yeah, if you wanted to just
one of the other questions?
When do you plan to inject?
So our target is to try to reach injection by end of 2027, early 2028.
That's great. That's great. Thank you so much, Brad. I think in the interest of time, we will wrap this up. And I just want to thank again my co-presenters here. Thank you to TNO for doing this really timely and informative study. And I do recommend you just go and you can download the report, and there's a lot more information in there. So thank you very much.
Thank you, everyone.
Thank you.
Thank you, everyone, for your time.